Welcome to our lecture video in hydraulics with the topic Hydrodynamics, forces developed by moving fluids. And in this video, we will focus on forces acting on a reducing bend. We will also answer the two examples from this handout. So here in this figure is a reducing bend wherein the entrance of the pipe has bigger diameter or greater diameter than the exit here. So what happens here is that there will be a force and pressure of the water or the liquid that goes inside the pipe, and since there will be a smaller diameter in the exit, there will be a resisting force, the opposing force F2, and the opposing pressure. We will also deal with the resisting forces R with its Y and X components. Also, we have to take note that although this reducing bend will be in a fixed position, the value for V1 is not the same with the value for V2. So the velocity at the entrance is not the same with the exit velocity. Why? It's because of the differences in the diameter. There will be a different area for the two. Even though the Q1 is equal to Q2, area 1 is different from the area 2. Therefore, the velocity will not be the same. So from this topic, we will deal with two forces, the static and the dynamic forces. And under the static forces, we have this formula, F is equal to area times the pressure. And for the dynamic forces, we have here the summation of F of x is equal to Q gamma over the acceleration of gravity times the x component of V2, the x component of V1, that is equal to F1 positive, so positive to the right, minus Rx, so Rx is to the left, and then negative F2 cosine theta. Negative because our F2 here in this figure goes to the left. And here we forgot to put the angle, the deflection angle theta. So this is theta. Now as for the summation of forces Fy, that is equal to Q gamma G, and that is multiplied with the y component of V2 minus the y component of V1. That is equal to Ry, positive upward, minus the F2 sine theta, being the F2 is downward. We will also deal here we will use the energy, the Bernoulli's energy theorem, wherein we get the velocity head, the pressure head, and the elevation head. So let's solve the examples. Let's start with example number 1. A 45 degrees 300 millimeters by 200 millimeters reducing bend in a level pipeline carries water at the rate of 280 liters per second. Determine the components of the force necessary to hold the bend in position. The pressure at the entrance is 345 kilopascal and the friction in the bend is negligible. So here we have a 45 degrees bend, reducing bend. So the deflection angle is 45 degrees. So theta here is equal to 45 degrees. So take note that theta starts from this side. So that is the deflection. It's not here. Rather, the deflection starts here. That is 45 degrees. And since this is a reducing bend, therefore the bigger diameter is in the entrance. this is the 300 mm diameter, and this is the 200 mm diameter. Then it carries water at the rate of 280 liters per second. So therefore, our Q here is equal to 280 liters per second, or that is 0.28 cubic meters per, or cubic meter per second. We need also to take note that the reducing band is in a level pipeline. So that means the figure that we're looking at is actually in top view. So the band is being laid in a level pipeline wherein the point 1 and point 2 are on the same elevation. Also, we will take note that the band is being held in position. So meaning the band is not moving at all. So we're looking for the components of the force necessary to hold the band in position. Components, meaning we're looking for the Rx and the Ry. So what's the formula from the handout? The formula there is Q gamma over G times the x component of V2 minus the x component of V1 equals F1 positive to the right minus Rx, so negative to the left. And then for the F2x, that is to the left, therefore that is negative F2 cosine of 45 degrees. Now as for the Ry, we have here Q gamma over G times V2y minus V1y is equal to the Ry positive upward, and then minus the F2 negative downward. So F2 sine 45 degrees. So that's the formula. So we need the values for the velocity. So from Q1 equals area 1, velocity 1, and that is also equal to Q2 of area 2, velocity 2. So Q1 is 0.28 equals pi over 4. Diameter here is 300 mm squared, and then velocity 1 equals pi over 4, 0.2, 200 mm diameter, that is V2. So what's now the value for V1? V1 here is equal to, so 0.28 times 4 all over pi times 0.3 squared. So 3.96. So 3.96 meter per second. Then V2 is equal to 8.91. So 8.91 meter per second. Then we need to find the V1x. So V1x is equal to V1 is equal to 3.96 meters per second. V2x is equal to, where's our V2? So V2x is to the right, so positive to the right. So V2 is 8.91 cosine 45. Next, V1y. So V1y is equal to 0 because our V1 is horizontal. Then V2x is equal to, so our V2 is upward. So that means upward positive here, so upward positive there. So V2y, should say V2y here, is equal to 8.91 sine 45 degrees. Okay, so we have our V1 and V2 x and 1 components. So let's go to the values of forces F1 and F2. How do we get the values for F1 and F2? So using the formula, F is equal to area times the pressure. Since given here is the P1 of 345 kilopascal, we need to find the value of P2 using the Bernoulli's energy theorem. So E1 is equal to E2. So velocity head plus the pressure head plus the elevation head equals the velocity head, the pressure head, plus the elevation head. Now, as for the head loss, it says here, friction in the bend is negligible, or the head loss is equal to 0. So there's no head loss. And we will cancel out Z1 and Z2 because they are on level pipeline, or that is on the same elevation, on same elevation. So the value for V1 is 3.96 squared all over 2 times 9.81 plus P1 is 345 over 9.81 equals V2. V2 is 8.91 squared all over 2 times 9.81 plus P sub 2 times the gamma 9.81. So P2 is now equal to 3.96 squared all over 2 times 9.81 plus 345 over 9.81 minus 8.91 squared all over 2 times 9.81 equals times 9.81. So 313.15 kilopascal. So we can now get the value for F1, area 1, P1, that is pi over 4, diameter 300 squared, and then 345 for the pressure, and then F2 so F2 is equal to area 1, area 2, so area 2 P2, so pi over 4, 0.2 squared, and then we have here the pressure 2 of 313.15 equals shift pi over 4 times 0.3 squared times 345. So 24.39. And then 0.2. 313.15 9.84. So we now have our F1 and F2. We can now substitute all values to our equation. So Q here is, what's the Q again? 0.28. So 0.28 gamma of 9.81 all over acceleration of gravity. We will be using 9.81, that is in kilonewton per cubic meter, because we're using kilonewton for the forces, times V2x. The V2x here is 8.91 cosine 45, 8.91 cosine 45 minus V1x, 3.96 equals, so equals F1 minus Rx minus F2 cosine 45. So F1, 24.39 minus the Rx minus 9.84 cosine 45. So Rx is equal to minus 9.84 cosine 45 minus 0.28, 8.91 cosine 45 minus 3.96. So 16.78 kilo Newton. Since that is positive, that means our Rx orientation here is correct. So Rx orientation to the left is correct. Next, for the Ry, that is 0.28, 9.81 all over 9.81 times V2y. V2y is 8.91 sine 45 minus 0. And that is equal to Ry minus F2 sine 45. So Ry minus F2 sine 45. Therefore, our Ry is equal to, so 0.28, 8.91 sine 45 minus, or rather plus, 9.84 sine 45. So 8.72 kilonewton. And since that is positive, it means the orientation here, that is upward, Ry, is correct. So this is upward. So that's for example number 1. Okay, so let's go to example number 2. The pipe bend shown is in a horizontal plane. So meaning they are the point 1 here and point 2, they are on the same elevation. So the bend shown is in a horizontal plane. A fluid weighing 8.615 kilonewton per cubic meters enters the bend with a velocity of 3.5 meters per second in a pressure of 280 kilopascal. Neglecting head loss, find the force required to hold the bend in place. So what we're looking for here is the force R. So we're looking for the resisting force R to hold the bend in place. Now to get the value of R, we will need the X and Y components of R. So X and Y components of R. So this is the entrance of the pipe having the diameter of 200 mm. So the water enters here with F1 and pressure of 280 kilopascal. So the pressure here, P1 is equal to 280 kilopascal. And then the force of the water will be in this direction. This is the F2 with the forces with the pressure P2 unknown. And then the velocity entrance here is horizontal. And then the exit goes out at an angle of 65 degrees. So given here a fluid, so gamma is equal to 8.615 kilonewton per cubic meter. So this is not water. So find the value of R. So we will use the formula again, that is Q gamma over G times V2x minus V1x. That is equal to the summation of forces. Summation of forces that is positive to the right, and that is positive F1. Now negative Rx, this is our Rx, negative. And then for the F2, you can observe that F2x have the same direction with F1, therefore F2 is positive to the right. So F2x, that will be F2 cosine of 65. Now for Ry, that is Q gamma over G V2y minus V1y equals summation of forces vertical, positive upward, Ry minus F2 is downward. So that will be negative F2 sine 65. Now as for the velocities, so for our velocity V1x is equal to V1, and that will be 3.5. So it says there 3.5 meter per second. Then V2x, for velocity 2x, so you see here that the x component of V2 is opposite V1. Therefore, that will be negative. So V2x is equal to negative V2 cosine 65. Next, V1y is equal to 0. And then V2y is equal to, it's upward. Upward here is positive. So V2 sine 65, positive. So to get the value for the velocities, P, so we don't have value for Q, but we were given the value for V. So therefore, we will use that, knowing that Q1 is equal to Q2, so that is equal to area 1, V1 equals pi over 4. What's the diameter here? 200 mm diameter. 0.2 squared times the velocity 3.5. So what is Q? Shift pi over 4 times 0.2 squared times 3.5. 0.11. 0.11 cubic meter per second. How about V2? This is also equal to pi over 4. What's the diameter and the exit? 80 mm diameter. So 0.08 squared V2. So V2 is equal to, so cancel out theta over 4 here. So V2 is 0.2 squared times 3.5 all over 0.08 squared. So V2 is 21.88. 21.88 meter per second. So we have now our velocity. Next, the forces. And we can get the value for the P2 from the energy theorem, Bernoulli's energy theorem. E1 equals E2. So V1 squared over 2G plus P1 over the gamma plus Z1 equals V2 squared over 2G plus P2 over gamma plus Z2. How about head loss? It says here neglecting head loss. So no head loss, but we cancel also Z2 here. Why? Because the pipe is in a horizontal plane, so this is in top view, and P1 and P2 have the same elevation. So they have same elevation with Z1 or 0.1. So V1 is 3.5 squared all over twice of gravity plus P1 here is, what's P1? 280 kilopascal all over. What's the gamma again? Gamma here is 8.615 equals V2 of 21.88 over 2 times 9.81 plus P2 over 8.615. Minus 21.88. Oh, squared. We forgot the square. So 3.5 squared over 2 times 9.81 plus 280 over 8.615 minus 21.88 squared over 2 times 9.81 times 8.615 . So that will be 75.26 kilopascal. And then we can get the forces now by F1 is equal to area 1 P1, and that is equal to the pi over 4 0.2 squared, and then the pressure of 280 kilopascal. And then F2 is equal to area 1 or area 2, and then P2 equals pi over 4 times 0.08 squared times 75.26 equals 8.615. 75.17. So 75.17. There. So 8.8 kilonewton. Point 377, that is 0.378. Then substitute all values to our formula, that is 0.11 for the Q gamma of 8.615 all over 9.81 times V2x. Remember that our V2x is negative V2, or that is 21.88. So that is negative 21.88 cosine of 65 minus the V1x of 3.5 equals positive F1 negative Rx positive F2 cosine 65. So F1 being 8.8 minus Rx positive F2 of 0.378, and that is cosine of 65. So Rx is equal to 8.8 plus 0.378 cosine 65 minus 0.11 times 8.615 all over 9.81 times negative 21.88 cosine 65 minus 3.5, so that is 10.19 kilonewton. Then for the y, so we have there 0.11 8.615 all over 9.81 times V2y. V2y is V2 sine 65 minus 0, or V2 is 21.88. So that is 21.88 sine 65 minus 0 equals Ry minus F2 sine 65. So Ry minus F2. F2 is 0.378 sine 65. So Ry is equal to 0.11 times 8.615 over 9.81 times 21.88 cosine 65 o sine 65 plus 0.378 sine 65. Oops. So plus 0.378 sine 65. So that will be 21 sine. Oh. So 9 point, there we go. So 21.88 sine 65. There. So 2 point so 2.26 kilonewton. So R is equal to square root of 10.19 squared plus 2.26 squared. So checking 0.11, 21 sine plus 0.378 sine 65, 2.26. Okay, so square root of 10.19 squared plus 2.26 squared, so that is 10.44. So R is equal to 10.44 kilonewton. So that's the value for R. So that's number 2. Okay, so that's all for this video.